This is Mrs. O'Neill for AP Chemistry, Chapter 5, Section 2, Part 2, Internal Energy in more detail. So the internal energy of a system can be one of two things: an actual reaction, like a combustion reaction, going from reactants to products, or it could be a process, like liquid H2O going to solid H2O. So I want to remind you that this internal system, or the internal energy of a system, is a change in energy. So again, that delta, it just means that we're going to subtract the final minus the initial. So the two different signs that it could have. If delta E, the change in energy, is greater than 0, means it has a positive value. That means the final energy of that system was greater than the amount of energy it started with. It means that the system must have absorbed energy from the surroundings, and it's called endergonic. That should remind you of a particular word you might have heard of in Chem 1. So if delta E is less than 0, it has a negative value. That means the final energy was less than the initial energy that system had. That means that system released energy into the surroundings, called exergonic. Again, endergonic and exergonic are two words you should have already somewhat be familiar with. So there's going to be a graph here I'm going to show you, and I suggest you draw and label them, but I also suggest you watch the video first and then go back and make your graph, because some of you might want to make one graph and put a whole bunch of things on it, and some of you might want to make 2 or 3 graphs and label just different components. Lots of stuff to talk about here. So this is what we call a reaction coordinate or reaction pathway. So here we have reactants and here we have products. And notice on the side here is the amount of energy, or we're going to call it also enthalpy, which is symbol is H. So this is the energy in kilojoules. This is the reactants, and always reactants are going to absorb enough energy to reach a peak on top of the hill and then come back down and make products. Now, sometimes that line stops here before the amount of energy it started with, and sometimes the line's going to come all the way down here, and the products are going to have less energy than the reactants it started with. So I'm going to label this as R for reactants, and I'm going to label this as P for products. So this hill that I talked about, so reactants have to absorb enough what's called activation energy to form this activated complex molecule. And that's a molecule that's kind of in between the reactants and products. It's kind of hard to explain. We will again explain that in a little bit more detail in the coming chapters. But right now, all you need to know is that the reactants need this much energy to reach this hill. And again, that's called activation energy. That's enough energy to make what's called the activated complex molecule. So let's explore this part of the graph first. This is considered the endergonic part of the graph. Why? Because we are absorbing energy. Okay, we are going up. We are absorbing energy. So we started out with 80 and now we have 240. So we've absorbed energy. So this is the initial energy. This was the final energy. Now let's look at that word endothermic. That endergonic should have reminded you of. So when we're absorbing energy, it is in the endothermic sense. So let's make sure of the sign. So if we take 240, that's our final, minus our initial of 80, we get a positive delta H. And again, a lot of times now, I know it's positive energy, but because it's heat energy, we're going to talk about delta H, the enthalpy, the heat energy, and that's going to be in the positive sense. Now let's look at the other part of the graph, the exergonic part of the graph. So now here's a little different. Here we're starting with 240 energy and we're going to about 160 energy. So this is the initial once we've made that activated complex, and our final now is forming our products of 160. So again, exothermic, right? Did exergonic remind you of exothermic? So heat is being released into the surroundings. So let's look at mathematically. So we're going to take the 160 minus the 240 we started with, and notice we have a negative delta H. So again, it's going to be a negative heat energy for exothermic reaction or exothermic process. So now let's talk about bonds. When we're truly talking about a reaction, we're going to take those bonds and we have to break them. So we have reactants and those bonds have to break apart, okay? They have to spread each other enough. Those atoms need to spread each other far enough from each other to actually break them in order to make, again, this activated complex. Well, then going down, we need to make those bonds. Now we're going to make new bonds to form our products. So I like to look at this. This was a mnemonic a student shared with me, and then I shared with the class. And I also suggest that anytime you have something that you put into mind to help you remember something, please share it with me so I can share it with the class and future classes. So if you look at this part of the graph, it looks like you're almost making a B, right? It's a starting of a B, so that's breaking bonds. And over here, it looks like we're making an M, so that's making bonds. So again, whether it be the visual or the actual words or looking at how to make a B and an M, so it's always going to be breaking and making. So we want to remember that the universe has two parts. The system that we're actually interested in, concerned with, and the surroundings is everything else. So endothermic reactions or endothermic process absorbs energy from the surroundings. Well, think about those ice packs. So if you take the ice pack, which is normally at room temperature, but then you break them, right? You have to like kind of break them a little bit or to get the reaction going on the inside. So on the inside of that pack, two solutions are mixing together and now it feels cold. Well, the reason it feels cold is because the reactants inside, in order to form products, have to absorb enough heat energy from the surroundings. And it's really the surroundings that we touch that we can feel the cold. Same thing with exothermic reactions or exothermic processes. They release energy into the surroundings. So think about a match. When I take a match and I light it, okay, it went from room temperature, now it's warm, right? That fire that's on the edge of that match is now releasing heat into the surroundings. That's why we feel the warmth, okay? So again, the system is what we're concerned with on the inside, and the surroundings is really what we can feel, and the rest of everything else. So now let's look at another visual, hopefully to get you to understand this. So this yellow box here is a system, and the white around it is the surroundings. So if our delta E is greater than 0, it's positive, that means the system must have absorbed heat energy in order to be endothermic, okay? So if this system is going to absorb heat energy, the surroundings is going to feel cold, okay? And that's going to be a positive sense. So this is an actual reaction of nitrogen and oxygen is going to absorb enough heat energy to get to the top of that hill, right? Enough activation energy to get to that top of the hill. And then now notice coming down, there's a lot less energy being released. So a lot of energy absorbed, a little energy released to form those products. So overall, your products have a heck of a lot more energy than the reactants you started with. So this overall reaction is considered endothermic because your products have more energy than the reactants. So those reactants absorbed that heat energy in order for that to happen. And if you look up here on the reaction, on the top left corner here, anytime I see endothermic or anytime I see a positive delta H, I always have heat as a reactant, and I put that right in the reaction or right in the equation to remind me of that, okay? So not only does it deal with reactions, it also deals with process, like I was saying about H2O. So let's think about these molecules, and let's think that they are in the solid state, H2O as a solid. And these dotted lines in between, where this one is labeled, that's called intermolecular forces between those molecules, the IMFs. So if this is solid H2O and I want to go to liquid, what's going to happen to the force of attraction between this H2O molecule and this H2O molecule? I hope you said it. It requires energy to be absorbed to melt the ice, to spread apart the forces of attraction between those H2O molecules. So think about this ice, right? Those molecules are real close together. So in order for those molecules to spread apart more, it has to absorb enough energy to start forming the H2O liquid, almost like breaking bonds. So even though we're only talking about the force of attraction between those two molecules, it's very similar like breaking bonds. So now let's go the other way. Again, our system is this yellow box, and if the energy is released into the surroundings, the white area all around, it's considered exothermic because now it has a negative value, okay? So now let's look at an actual reaction diagram, a combustion reaction. So we have our methane gas burning with the oxygen. It's going to absorb, look at this, it absorbs a little bit of energy in order to reach its activated complex, but it's going to release so much more energy to form those products. So heat is released, or products have less energy than it starts with. So again, if you look up here at the actual balanced equation, anytime I see exothermic or a negative delta H, I always put heat as a product, just as a reminder that heat is being released. So now it's a product, it's given away. Let's look at these IMFs again. Again, we're talking about H2O molecules, but now let's pretend that this is a liquid. Okay, so now these molecules are in the liquid phase, and now we want to bring them to the solid phase. So what's going to happen to the force of attraction here, where this one is labeled? What's going to happen to those IMFs? I hope you said it. It requires energy to be released to form the ice, to bring the forces of attraction closer together between those H2O molecules. So it's almost like we're making those bonds or making those IMFs closer together with those water H2O molecules. Okay, so we want to remember, hopefully this helps you understand now that measurement of energy has three parts. The number and the unit that you're used to, but now we have to give it a sign, endo and exothermic, again, positive for endo, negative for exo. And remember, it's not always just about reactions, it's about processes as well. So give this some thought. Again, pause the video, see if you can answer this question. Hopefully you said endothermic. So now let's look at this reaction. So here is it in the exothermic sense, right? So we have hydrogen and oxygen. It's going to absorb enough energy. It's going to release a lot more energy. So our products have less energy than the reactants it started with. So that's exothermic. If I flip it, if you notice, all I did was take this picture and flip it, so everything is backwards. But now we've taken water, and now we have to absorb a heck of a lot more energy than the energy being released. So now our products here of hydrogen and oxygen have more energy than the energy that it started with. So they're always going to be opposite of each other. Okay, hopefully you understand this, and if not, I am looking forward to questions. Again, this is a video you want to keep in the back of your head, star it, highlight it, email it to yourself, and always be reminded that this is going to be information you're going to need from now until the end of the course. This exo-endo, the IMFs, the positive negative signs, all those things are going to be really important.